Bismillahirrahmanirrahim. In this lecture, we are going to describe the Taylor and Maclaurin series. By this series, we can expand each and every function. That functions can be approximated with the help of this expansion. So if we want to expand a function, we can use this series. So there are the three major topics here. One is the why we need the Taylor and Maclaurin series. This is motivation. Then we have to discuss the expansion, Taylor expansion. Then we have to express the Maclaurin series, and few examples are to be discussed. This is the material from chapter number 3 of the book, and a reading assignment is given to you which is related with the chapter number 4. So you have to cover the chapter number 4, start reading in chapter number 4 and discuss the things before moving to the next presentation to me. Now, we can easily compute the expressions like this expression. This is known as arithmetic expression. This arithmetic expression can be expressed by any series. Arithmetic expression, or if we have an algebraic expression, we may have the both type of expression. Algebraic expression. These expressions, we can have the calculations of this expression with the help of simple calculators. But there are some functions which are quite complicated, and we cannot expand that functions with the help of simple calculations. So in that case, we need some expansions through the Taylor and Maclaurin series. Like we can express under the root 4.1 by Taylor series. We can express sine 0.6 with the help of a Taylor series. So we can expand these functions with the help of Taylor series. But whatever we are doing with the Taylor series is an approximation. Means we are going to find out the approximate values of these expressions. So why we are going to express these expression with the help of approximation? The reason is we are going to learn very simple example here, but we have to extend this series for expanding the more complex problems where the direct solution or algebraic solution is not possible. So with the simple example, we are learning how to expand the simple functions. Then we will expand the complicated functions with the help of the same series. So that is the way that we are going to solve the functions. Achha, this is a note or the remarks. Whatever we are going to use as an angle, we have to assume it in radians unless it is stated. So suppose we are sine 30. Sine 30 is in degree. Sine 30 is in degree, but if we are not saying that this is the degrees, so that will not be an acceptable solution. Like we are going to expand 0.6. 0.6 is what? Sine 0.6. Sine 0.6 is in the radians. So this angle is in the radians. So whatever we are going to express here in the form of an angle, that angle will be assumed as the angle in the radians. This series is called Taylor series. Every function fx is what? Fx is a function. every function can be expressed with the help of this series. What this series is saying that, and we are going to expand the series at A. At A means suppose we are interested in sine 0.6. Suppose we are interested the sine 0.6. So your value of x is 0.6. And we are interested to expand this at any region A. So this function can be expanded with the help of this series. What this series is, fa is the actual value of the function. In not 0.6, we are not taking the first term as sine 0.6 because a is not 0.6. A is any number at which the value of sine is available. Suppose we already know the sine 0.1, so we can expand this 0.6 with the help of sine 0.1. So fa is the function value at a. What is f dash a? F dash a is the value of the function's derivative at a and x minus a. X minus a is what? The value of the variable x minus the point at which we are expanding the series. Then the second derivative of the function at a by 2 factorial, x minus a whole square, and so on. Third derivative of the function at 3 factorial, x minus a whole cube. So suppose I am interested in the kth term in this series, then the kth term in this series can be represented by f k a. What is f k? It is the kth derivative of the function at a divided by k factorial. And what will be there? There will be x minus a raised to the power k. X minus a raised to the power a, and so on. So at any point we can represent this by this function. So every function can be represented with the help of this expansion. This expansion can also be written as in the form of sigma notation. This can be written as fa. And then we have similarities among all terms. What similarities you are facing in all terms? We have the function's derivative. F, suppose I am representing it fi, ith derivative of a. Ith derivative of the function at a. This is what? This is ith derivative of the function at a divided by I factorial and x minus a raised to the power I. And we have to sum it. Summing start from 1 and up to, if it is an infinite series, then it is sum up to infinity. If we are going to represent this by the kth term only, so you can represent it as equal to 1 to k. So this is called expansion of the function by Taylor series. So we can expand this function with the help of the, I can close this term into the sigma. On the left hand side, what we have? On the left hand side, we have fx. Fx can be represented with this expression, and this expression we have fa and summation of this. I can also include this term into the sigma. How? We can include this into the sigma because it has the derivative term will be the 0, and 0 factorial will becomes 1, or x minus a raised to the power 0 becomes 1. So I can include this term in the sigma But if I include that term with the sigma, this will be becomes 0 to infinity. Instead of 1 to infinity, we will have 0 to infinity. So this is the way to write down the series into sigma notation. I am representing the sigma notation uh, in a equation. This solution can be represented with the help of this expansion. Taylor series expansion, instead of separate first term, the separate first term is included. K factorial. 0 factorial, the first term will be what? 0 factorial. 0 factorial will be a 1. Fk means the kth derivative of the function at a. So this is one term. This is a separate term. Fk, the kth derivative of the function at a, multiply by x minus a raised to the power k and 1 upon k factorial, k is equal to 0 to infinity. If the series converges, we can write down k factorial fka x minus a k is equal to 0 to infinity. This is equal to fx. So we can write down either the series in the expanded form. This is the expanded form of the series, and this is the expanded form of the series. And this is the sigma form or the summation notation of the series. Now we have to cover the one or two examples of this expansion. And before going to cover the example, I'm going to describe the Maclaurin series. So what is the difference between the Taylor series and the Maclaurin series? Taylor and Maclaurin series, very few difference among these two we have. Only the A is 0. In the Maclaurin series, the A is 0. If the A is 0, then a Taylor series is called a Maclaurin series. The Taylor series is called a Maclaurin series. The Maclaurin series expansion is simple. Instead of FA, we have F0, F dash 0 times X, because A is 0. Earlier, I was X minus A there. So if A is 0, then X minus A becomes X. Here I have X minus A whole square. If A is 0, then it becomes X square and so on. So X cube, X4. So it is quite simple as compared to the Taylor series. So in the Maclaurin series and in the Taylor series, there is a very simple difference among these two series. Maclaurin just defined the Taylor series with the value of A0. So if we put the value A0 into the Taylor series, then the series is referred to as Maclaurin series. The kth term in the Maclaurin series can be represented as Fk0. What is Fk0 means? The kth derivative of the function at 0 divided by the k factorial multiply by x ki power k and plus so on. So we can represent this series into the sigma notation. This is the simplified sigma notation of Maclaurin series. The Maclaurin series is 1 upon k factorial fk0 x e power 0. The fk0 means the zero derivative. Zero derivative means the actual function. X e power 0 becomes 1. So in the first term, I have 1, 0 factorial is 1. So in the first term, I have F0. The second term, when I put k is equal to 1 into the series, this becomes the f dash 0 times x and so on. The remaining terms we will get by just expanding this sigma. Now obtain the Maclaurin series for this expansion, e raised to the power. So now we have to expand the Maclaurin series with the help of e raised to the power x. So in the Maclaurin series, the value of a is 0. So what the Maclaurin series is, my Maclaurin series needs f dash x. F dash x is equal to e raised to the power x. F double dash x f2. I'm just representing f2. This is not f square. This is the second derivative of x. It is again e raised to the power x. If I am interested in fkx is equal to e raised to the power x. So all the derivative of these functions are, this is a very simple function. In this function, all derivative of these functions are same. But we have to calculate this f dash 0. Any first derivative at 0 is equal to the e raised to the power 0. And e raised to the power 0 becomes 1. Then we need f dash f square, second derivative at 0. This will again be the e raised to the power 0 is 1. And the kth derivative at 0 is again, because e raised to the power 0 is 1, is equal to 1. So all derivatives are 1. Now, what was the expansion? Your expansion was quite simple. Your expansion was fx is equal to summation k is equal to 0 to infinity f k 0 divided by 0 factorial and xk power k. This can be written as, when we put k is equal to 0, so this will becomes f00 divided by 0 factorial. This is not 0 factorial, this is k factorial. Here we have a k factorial, but when I put the value of k0, then in denominator we have 0 factorial and x raised to the power 0. This is the first term in the Maclaurin series. Then we have f10 divided by 1 factorial and x raised to the power 1 plus so on. Finally, we have kth derivative of the function and then put 0, k factorial x raised to the power k plus so on in up to infinity. So what is the value of f00 means the function itself, f0. It is what? It is f0 basically. f0 means e raised to the power 0 plus x raised to the power 0 becomes 1, 0 factorial becomes 1. So it is f00 means actual function. f10 is 1. So 1 upon 1 factorial is 1 and x plus this is 1 upon 2 factorial. So what we can say that x square it is equal to x square upon 2 factorial. This is x square upon 2 factorial plus so on x cube upon 3 factorial, x4 upon 4 factorial, and so on. So e raised to the power 0 becomes 1. So I can simply represent this as 1 plus x square upon 2 factorial plus x cube upon 3 factorial plus so on, x4 upon 4 factorial plus so on. This is equal to what? This is equal to fx. And in reality, fx is what? It is e raised to the power x. So you can have a Maclaurin expansion of e raised to the power x. Every e raised to the power x can be represented by this expansion. Suppose I am interested in e raised to the power 0.5. So e raised to the power 0.5 can be approximated by 1 plus 0.5 plus 0.5 square divided by 2 factorial plus 0.5 whole cube divided by 3 factorial plus 0.5 raised to the power 4 divided by 4 factorial and so on. If I need a very accurate solution of that, so I can expand this up to the as larger number of term as we can. Okay.